an older idea, really, that there are different kinds of uncertainty. There is the kind of uncertainty you get in roulette. You don't know which number it's going to end up on, but you know it's going to end up on a number. And there is this kind of uncertainty you get on the stock market. Is it going to crash or not? Or, indeed, is a new technology as innovative and as game-changing as the internet going to arrive? So the problem here is that black swans are about real uncertainty, not just that we don't know the probability of uncertainty. And I can give you a lot of nice confidence intervals and statistical caveats about everything I've been saying up until now. But when you come to black swans, and I think Nassim is right, we have a problem that traditional statistics might actually be a bit wrong. He calls it the ludic fallacy. He thinks that we tend to think of it as numbers in a game. That it's a well-defined probability, but it might actually be completely undefined. Well, let's just jump to this little example. This is my colleague Peter Taylor's nice example. You know these urn models that we tend to harass you with in statistics courses. You have an urn and you put in 10 black balls and 10 white balls. What's the probability of getting a black ball when picking it out on the urn? Yeah?
1, because you've got black paint in the urn.
Okay, now you're kind of cheating here, but you're on the right wavelength. Peter's example involves a little demon, a relative to Maxwell's demon and all that. So this little demon walks up to the urn and does something to it. What's the probability now? Let's assume you didn't get to pour your black paint into the urn. Before that, we would probably say that, oh, it's 50-50. But now the demon has done it. He might have listened to you and poured black paint into it.
Or he might put white paint, or he might have...
He might put a frog into it.
Yeah.
The problem is, how do we even define the probabilities here? And this goes back to the definition of probability in mathematics, which usually, if you use at least the Kolmogorov approach, it means that you have a certain space of outcomes, and then you distribute probability according across it, and if you're a rational person, you then update it in the right way. But what the demon does is he changes the outcome space somehow, and we don't have information about that. And that is very problematic for a traditional models of probability, and it's actually very problematic for most problems of rationality. It was very fun seeing Peter giving a talk about this. You can normally tell that the talk is good because people start debating among themselves, especially afterwards. But here the debate started while he was giving the talk among the philosophers. They really solved the problem. And they're also trying to come up with solutions, most of which doesn't seem to work that well. And this goes back, of course, to the Rumsfeld quadrangle, with this corner with Zizek pointed out. So we got the stuff we know, and then the stuff we don't know, and then, of course, the dangerous unknowns. And Zizek pointed out that, and then of course with stuff we know but choose to ignore, and that's a great example of why Rumsfeld et al. Ended up in trouble. But the black swans, they're not just about the known unknowns. So we have these extreme outliers, but when we have outliers because the game's completely changed. And they're rather tricky because when it comes to disasters, normally we like to have a kind of probability estimate to think about it. But when we can't even put a number on it, when we are going to, at this point, some people just throw up their arms in despair and say, oh, you can't speak about it, which doesn't work. Or you just move to an emotional state. Well, it would be too horrible to contemplate, so let's put a lot of resources into it. I think there are ways of doing robust reasoning about this, but this is actually a very interesting area of current research. So I'm going to kind of get back to it a bit roundabout, because I don't want to run out too much of time. Okay, so in general, of course, handling these new rules is interesting, because you might make probability estimates by guessing. So this was right after a conference last summer in Oxford about global catastrophic risks. So this is online where it's readable. So this is where delegates were asked to give probabilities for different levels of global disasters. So this would be that there is more than 1 million killed in an act of nuclear terrorism, and you get the probability, the median probability of about 15% of that happening this century. They assigned 1% chance of more than 1 billion dead due to nuclear terrorism, and 0.03% chance of total extinction due to nuclear terrorism. What was this based on? Well, hunches individually, assumptions based on the talks. So is this a rational probability estimate? Not really. I think we can see this as kind of level of concern of a somewhat initiated audience. But again, there is interesting problems here. So this is, for example, killed in the single biggest natural pandemic, and more than 1 billion, 60%. But as somebody remarked right after conference, well, actually, the AIDS pandemic is well on its way. It's probably 100% certain to have more than that number of dead at the end of the century. So we seem to, although we have heard lectures about the same subject for several days, we still underestimated it. On the other hand, here is total number of people killed by superintelligent AI. And now the estimates were all over the place because people can't really agree on it. It's a weird problem, it's a silly problem. It's a problem that many people haven't thought about, or they have thought about it within very strange contexts. So for example, in most of them, you had a kind of rule of that the biggest one, the second one, and third had a kind of same ratio. Here it's about equal. Everybody giving it between 5 and 10% because we actually don't know. So at the very least, we get a sense that this problem is something where the audience had a very different cognitive structure. So overall, this little exam produced a median risk of total human extinction of 19%. But that number, that's a number put on a quite imponderable thing. Just by having this conference, I hope we actually reduce the probability a bit by getting people to network, work together, and start thinking about some solutions. We got some interesting discussions going, for example, thanks to it. So even making a survey might actually upset the numbers. We got a little probability estimate board back at the Institute, where we also have this kind of probability for human extinction, us winning various grants, on Obama winning the US election, the Piracy Party getting into parliament and things like that, where we try to train ourselves to make good probability estimates. It's surprisingly hard. So overall, thinking about this kind of problems, we can also use scenarios, which are dangerous because when one should describe a very good scenario, people start believing that it's more likely. Everybody has seen Mad Max or some other post-apocalyptic movie about how the world after a nuclear war is supposed to work. So suddenly people believe that is a more likely future than it would be just in general. So we have a problem that our stories might be shaping quite a lot of this. And this is very problematic when it comes to black swans because they are tend, by definition, not to fit any of our preconceived stories. But it gets even worse. Yeah. Well, the dragons. So one great example is, of course, the Large Hadron Collider, which might or might not cause something like this. And of course, we got a very reassuring quote here from Michio Kaku saying that due to the uncertainty principle, well, it could also produce dragons. Which I think is completely all right, because thermodynamic miracles actually do occur. Well, this is not water boiling because you put it on a piece of ice. This is actually liquid air, but so it's a bit of cheating. But a thermodynamic miracle, that's something that's allowed by physics but just exceedingly improbable. A standard example in any textbook is that all the air in the room randomly would bounce into that corner, leaving us to asphyxiate. Or, for that matter, that the random collisions of atoms in the ice, tea kettle, and water produce a situation where all the energy goes from the ice to the water to boil it. It's entirely allowed by the laws of physics. It doesn't really break thermodynamics, because thermodynamics is a statistical law. It only works on average. And in this case, everything behaves very nicely according to normal distributions, which are in this case very normal. The deviations you get in energy level in that water are going to be exceedingly tiny. Again, this is a standard exercise in textbooks on statistical mechanics and thermodynamics to calculate. And you can see that there is no practical chance whatsoever for getting that water to boil. So we don't need to calculate how many millimoles of risk we have from the air moving around and asphyxiating us. So the dragons are possible, but they're not going to be happening really. But on the other hand, the concerns people had about the Large Hadron Collider were a bit more solid than that. It might create a black hole. Well, how do we calculate the probability of that? Well, based on our understanding of physics. Okay, and our understanding of physics suggests that it shouldn't be a problem, except that we built the accelerator to test our understanding of physics. So you need to come up with some better